let's go ahead.
It's time for break now.
Almost time for a break. Okay. Um, I can't apologize enough for my bad handwriting. If you write worse than me, probably you will be a physician. Okay, let me tell you what you're looking at. Let me tell you what you're looking at. Tao, my friend, let me tell you what you're looking at right here. You're looking at this scenario here, which repeats itself almost in 90% of the commercial industrial buildings. That what you're looking at is typically repeat itself in 90% of any commercial industrial building. You have a high voltage, HP for high voltage. If you guys want to write the terminology, always. You guys remember when we went to Boston Scientific? Did you see them where it says HP and LP panels? That's exactly what you're looking at. HP high voltage, LP low voltage. And you have 480 voltage system, always, almost always 480 for this panel, through a transformer down to 208. Typical, as I said, 90% of the time in the US, you're going to find this scenario. And the reason for this, because we haven't decided in the US to get rid of the 120 208 and go to 230. So we can't burn the receptacles at 277, so you have to burn them at 120. Any question about this scenario? And literally, they will be in the electrical room, dusted the same way that I'm showing them. This will be in the wall. Right next to it, it will be a transformer. On the other side, it will be a 208. And these guys will be within probably 10 to 25 feet of each other, physically, mechanically, for the most part. Any question, guys, about this? Is a physical location of what we're going to be doing. Cool? You guys are going to have this one in your project the same way. Any question, guys, about this? In our project, as a matter of fact, the overcam protection device is going to be where? For the transformer in a different room. We don't have this panel. That will be our switch gear, and it will be located right in here on a different location. Okay, so that's the physical location. This is the schematics of that system, or the one-line diagram for the system. So take the following. I have a high voltage overcam protection device, feeder, going to a transformer, 480 on one side, 208, 120 on the other side, going down to a panel, low voltage panel, 208, 120 panel, and I need to size these 5 things. Number 1, the size of the transformer, always 3-phase, always delta 480 on the primary, always Y 208, 120 on the secondary, typical. So almost always. This is, you're going to find a delta here, always a delta, and almost a Y in that secondary. Let me read it one more time. 3-phase, 480, 208, 120 transformer. We need to size it. Then after we size it, we need to go size the overcam protection device that protects it and the feeder that feeds the transformer, which is basically this deal here. Then we're going to go out to the secondary, size the secondary conductors, and at the same time, it will be the feeder for the lighting panel, which is this deal here. And then we're going to find the overcam protection device for the panel and the panel size itself. Cool? That's typical. Very typical. Cool? So that's what we're going to, and then from the low voltage panel, you're going to be feeding receptacles. This is a receptacle, believe it or not. This is a receptacle. That's the only reason why we do this, to feed receptacles. Cool? Lights, we can burn them at 277. Okay. Before I move ahead, I know I'm ahead of myself. Can you guys change this homework into, I'm going to give you a homework, the same thing. We're going to do a homework number 8. We're going to start with 105 kVA. I'll get over this in a second, the homework. But it's just number 8. Here's what we're going to size for. So how do we size a receptacle transformer? You want to size a receptacle, since it's mostly receptacle transformer, we're going to size it based on the receptacle load that we have. Okay, so I assumed when you guys did your receptacles in the building, you came up with 200 receptacles. Duplex, single duplex or quad, single or duplex, 200 M. Multi-outlet assembly, 60 of them continuous. Multi-outlet assembly, 70 feet of non-continuous. Do you guys remember the multi-outlet assembly? This is this, right here in front of you. I decided, Chad Curdy, in this building to put 200 receptacles, and then, just to spice it up for you, I also decided to put multi-outlet assemblies. Continuous, this is continuous, 60 feet of them, and the non-continuous is 70. Okay, that's it. And I want to size based on this receptacle load. Based on this receptacle load, I need to size the receptacle transformer, the receptacle panel, and all the stuff in between. Any question, guys, about what you're looking at? When we size anything, Chris, remember the load calculation that you guys did with me? And when we did the load calculation, you came up a lot with KVA for the transformer, KVA for the receptacle panel, right? You did the load calculation, you came up with KVA for the receptacle panel. That's exactly what we're trying to do. I'm trying to find the KVA for the receptacle panel. Cool? Any question about the given before I move anywhere else? Any question about the given? This is what you have. Everybody knows the criteria for all this stuff. I mean, you can almost do the refer this one into transformer. This will be number 1 here, the transformer. Let's just put with this will be number 3, right? Number 3. This is number 3. This one would be number 3. This will be number 6, right?
Yeah, I just did a quick question.
Give me 1 second here. Let me just and this one would be number. This one would be number 2, right? This one will be number overcam protection device right here. This would be number 5. I'm just trying to get that one. And what else do we have? The panel itself. The panel itself will be number 4. Did I miss anything? So 1, 2, 3, 4, 5, 6. This is how these are related to each other. Yes, sir.
And that's the process. That's how it's got to start with the transport.
Yeah. Can I do? Yeah. Do they have to be in this order? Not really. But the first step is 1. You've got to find 1. And then after that, you can make 5 before 4, and you know what I mean? But 1 is the first step that you have to do. Any question, guys, about these? Can I have thumbs up, Chad? We know what we're looking at. Tom, my friend, Jackson, Phil. Okay. Okay, let's go ahead and start. Now, I put 220.14H and 220.14I. This is 220.14I. These are the code. 220.14I. Okay, from 220.14H and 220.14I, Chris is going to go check them for me. You're going to find the following. You're going to do the calculation on the receptacles. It will tell you guys in a commercial industrial building, every receptacle is assumed to be at how many volt amps? 180. So I have 200 multiplied by 180 volt, right? Then multi-outlet assembly continuous. This one MOA, not Mall of America. This is multi-outlet assembly continuous. And I have 60 of them. If they're continuous, it tells you have to multiply them by 180 for every 1 foot. For every 1 foot. Mall of America non-continuous. Multi-outlet assembly non-continuous. Non-continuous, they say take every 5, divide it by 5, and then multiply it by 180. You guys remember that? We did it in the fall. How to do calculation for receptacles and how to do calculation for multi-outlet assembly, right? And then when you're done, make sure you add them up. And that will end up with 49320 volt amp. Any question, guys, about this? Straightforward. That's a calculation that you have to do from 220.14H and I. Any question? And we did these in the fall, if you guys remember that. I know the fall has been a long time ago. I probably forgot. H is multi-outlet assembly and I is receptacles. Okay. Any question, guys, about this? Straightforward. Please correct me if I did the math wrong. Then, Chris, non-dwelling receptacles. When you do the calculation on non-dwelling receptacles, you take 220.44, you derate them based on 220.44. You need to derate based on 220.44. Okay. I derated all of them here. So we're going to take the 49320 320. From this table, it will tell you the first 10, leave them alone, 10,000, leave them alone. Anything higher than 10,000, which is in this case will be 4,9,3,2,0 minus 10,000. What do you do with them? You have to cut them by half. So I have to multiply this by 0.5, okay? And then add them up. So if you do that and you do all the math, you end up with 29.6 kVA. And remember, I divided by 1,000. So the first 10,000, don't forget to add them up. The first 10,000, leave them alone. Anything higher than 10,000 multiplied by 0.5, then add them up. Add the 10 to the stuff that you cut by 50%. That will get you 29.6. 29.6. And I moved into kVA now. I moved into kVA. From now already, but we know how to move from VA to kVA. That shouldn't be a divide by 1,000, right? VA to kVA. Any question, guys, about 29.6 kVA? Any question? That's what they call it, the demand. So this number is 49 kVA. Look at the, if you size based, a lot of people, if you size based on, if you guys convert this one into, that would be 49.3 kVA. Look at this. If you want to size the transformer based on 49.3 kVA versus 29, you're going to end up a big fat transformer. They allow you the derating because highly unlikely that all the receptacles are going to be used at the same time. That's smarter than Chad decided. But the first 10 are sacred cow. We leave them alone. We don't want to mess with them. Okay, any question, guys, about this? Step number 2. Let me know when I can move to step number 3. So we did the calculation here. Okay. The second thing, guys, we need to go to DeWalt 7-7. Could you please go to DeWalt 7-7? If you guys do DeWalt 7-7, if you guys go there, you're going to find a bunch of really interesting table. If you don't have cut sheets about your transformers, everybody is 7-7. Can you guys look at that? 7-7 DeWalt. So we were looking at I am looking at 29.6 kVA, 29.6 kVA. From 29.6 kVA, if you guys go to DeWalt, in the first column gives you the standard industry kVA size of 3-phase transformers, right? So I have 29.6. What's my next standard kVA? What's my next standard kVA? Allowable 30, right? Everybody can see that? 30 kVA. 30 kVA. The next standard is 30 kVA. Now, Chris, say you decided to add another 25% for future expansion. First, you add them on the 29.6, then you size your transformer. That's where you have to make up your mind. I made up my mind, that's all what I need on this transformers, and I'm done. So that will be a 30 kVA transformer. Do me a favor, from the same table, guys, can you guys go to 30 kVA under the 208? What's the current under 208? 83.3. They give you the full load current on both the primary and the secondary. Under 208, your full load current is 83.3. Chris, under 480, what's your full load current? From the table. 36.1. So they're giving you the full load current of multiple voltages. You can pick whichever voltage you have. So we have 480 and 208, so you can find the full load current directly. You don't need to do the math on that. So from here, I'm just going to say for the 208 side, the 208 volt. So the 208 volt side, and just for the heck of it, the 208 volt side was 83.3 amps, and for the 480 side, directly from this baby, for the 480 side voltage, the 480 was 36.1 amp. I don't need to even, how did they come up with this? You took the kVA divided by the voltage, 1.73. So you're not rocket science. But you can, from this size, you can find all this stuff directly. So my actual size is 30 kVA. My actual size is 30 kVA. 30 kVA. Any question, guys, about the 30 kVA size that we have? Okay, so now we found the size of a transformer that we need to buy. The second thing you need to do is find, now Nick, do I need to go to the overconduction device chat? No, you could have sized the conductor, you could have sized, really, from after, the first step is must. The second one, you can do them in any order. Okay, primary overconduction device, I primary. So what I did for the I primary, guys, you either do two things. You take the 30K, divide by 1.73 times 480, and that should get you the same amount, 36.1 amps. Does that sound familiar to you from what we got from DeWalt, give or take? So either you do the calculation, I like you to do the calculation, or you can grab it from DeWalt. Okay. So that's the first thing to do, is to find the full load current on the primary side. And what we're trying to size here, Nick, is that overconduction device that protects the transformer. Now, Chris, if you go to table 450.3b for any transformer, if you guys go to table 450.3b, it will tell you that your multiplier is going to be 2.5 multiplied by the full load current, which is 36.1, and I would have a 90 amps, and then you need to take your 90 amps into 4.6, and we hit the jackpot, 90 amps. If it's not a standard, Chris, what do? You go down, because they don't allow you to go up if you go to the table. Now this is assuming primary and secondary protection, guys. Primary and secondary protection. We're doing a primary and secondary protection for the transformer.
Do you have any standard figure you use for the efficiency?
For transformers, usually 99.9. Transformers are very efficient because they don't have rotating things. It's all magnetic. So
just in the other exercises, we were using efficiencies of 6.5 and other percentages.
Oh, you mean the impedance?
Yeah, I'm sorry.
The impedance. Okay. Yes, you have to have the impedance, but not from this table. Then you have to go to the manufacturers to find the impedance. Unfortunately, you take the 30 kVA to Cutler hammer and find yourself a Cutler hammer transformer, and then it will list the impedance for it. I'm not giving it to you here though. Any question, guys, about the primary overconduction device? So what's my primary, guys? 90 amps. I size my circuit breaker or fuse, right? It's circuit breaker or fuse. In this case, I'm using a circuit breaker. Any question about the primary overconduction device? Let me know when you guys are done with this.
Did you really go down based on the mathematics that we get here?
I went down because if you go to 450.3b, it doesn't have note number 1. Remember, guys, note number 1? And note number 1 tells you if it's not a standard, go up. So if it doesn't tell you to go up, let's go back to the 3 options. Anybody remember the 3 options? If you can't go up, custom design yourself. In this case, it's 90, so you really hit the jackpot. But say if it was 89. No, it was 91. Say it was 91. Here's your option number 1. Either you go down to 90, or you custom design a fuse and pay an arm and leg for it for 91, or you go to the bar, drink, and cry because you could not find your fuse or circuit breaker. The third one is mine. Just any question, guys, about this? So if it doesn't allow you to go up, the default is you go down because you can't stay where you are. Can I go to the next one, Dustin? Cool. Okay. Primary feeder. Now we're going to find the feeder that feeds that transformer, guys. Primary feeder. I want you to do the math for me. The primary feeder, I will take the 36.1. Remember that, guys, full load amp? The 36.1. Primary feeder. is the primary feeder is 36.1, right? Then, right, this is amps. Then I'm going to take the 36.1 multiply. Now here's where you have to make a decision. 36.1, if I want to take full advantage of my transformer and take the full 36.1 amps, then I have to multiply by 1.25 because continuous becomes continuous load. So I'm going to multiply this by 1.25 for continuous load. Chris, what is this one for? Continuous load, 1.25. Okay, I didn't do the math. I need somebody to do the math for me here. What's 1.25 times 36? 1.25 times 36.1 equal, that will get me 45.1. 45.1 amp. Okay, so you got 45.1 amp. I just multiply it by this because I assume it's continuous. Then you take the 45.1 amps, take it to 310.15B16, and this is a table under 75-degree column. You always go to 75, Chris. That's for your default because we're three-phase. Equipment three-phase almost always rated the logs for 75 degree. No question asked. We're three-phase here. So you go to 75. What's the I don't have this one. What's the full load current for the what's the conductor size? Anybody? Number 8. Still number 8? Good grief, I thought it goes up to 50 amp. Okay, number 8. Now how many conductors though?
3.
Thank you. I need 3 conductors. Number 8. A, W, G, T, H, H, M. That's it. Oops. So 3 conductors, number 8, AWG, THHL. Now assuming it's continuous load and we size that baby. Okay. Any questions about this? On the secondary side, Chris, let's do this. On the secondary side, I know what the full load current secondary, without even looking at it, it's 83.3. But I still would like you guys to do it. So 30 kVA divide by 1.73 times. Now we move to the secondary 208. So if you do the math, give or take, that will be 83.3 amps. 83.3 amps. Now the same thing. So we need number 3 number 3, I'm sizing the receptacle panel now. I'm using this secondary current to size the receptacle panel. The low voltage panel 28120. Cool. Here's 83.3. Now if I'm to take full advantage of continuous load on this, full advantage, continuous load, I would like to multiply it by 1.25 to take the full advantage. So take 1.25, multiply this by 83.3. I did not do this math, so I need somebody to do it. 104.2 amps. Thank you, Oladipo. Okay. Why did I multiply by 1.25, Chris? I would like to assume that my panel, after I installed it, it can be used fully to the 83 amps. But if it's used fully to the 83.3 amps, you have to allow continuous load of 25% extra there. Okay? Then, the last one, guys, is to take, remember, we are sizing a panel. We're not sizing an overcap protection device. We're sizing a panel. So if you guys go to did I do it in the second slide? No, I did not. I used it right here. So right here, you're going to take the 104, step number 3, 0.2 Oladipo, take it to DeWalt. What was the DeWalt that talk about panels? DeWalt that talks about 312. Thank you. 3-12 or 3-13, depending how high you go. Chris, what's the next standard panel?
125.
Thank you. 125 amp. So no matter what, your next standard panel is 125 amp. Make sense? Now look at this. I have a 125 amp panel tied to an 83 amp 0.3 transformer. Kind of, it's like defeating the purpose. You have more amps in the panel than the transformer, but the reason for this because of continuous load. We're going to allow the continuous load on 25% on the panel. Any question, guys? So my panel size is 125. Now we go by 125, 28, 123 phase panel. Okay. This is what you guys are going to be, William, I have a piece right in front of you. This is what you guys are going to be doing for me in the project when you size the transformer, receptacle transformer. Can I move? Yeah. All right. Now the fourth thing that we need to size, receptacle panel overcam protection device. Receptacle, now this one is receptacle panel overcam protection device, and Nick, the same device is actually also the overcam protection device for the transformer, right? Let's go pick that one right here. Can you guys see this baby here has two functions? That's the main for the panel and also could be considered the secondary for the transformer. Can you guys see that? Really, technically, the secondary for the transformer have to be right in here, guys, right? The terms. So, but we're assuming we have two primary and secondary protection for this transformer. So that we'll leave it at this. Receptacle overcam protection device. So where are we here? So we size the panels. Then I'm going to do the same thing. For the overcam protection device, I'm going to do the same thing. If you have a circuit breaker, Nick and Dustin, and you need to, how much can you pull out of this circuit breaker continuous? 80%. So that's why we also multiply it by 1.25. So I'm going to go multiply this. 1.25 times the secondary conductor was 83.3 amps. That will give me 104.1. What was the 104.2? Thank you. And this is the step one, exactly like we sized the panel, guys. Then you go 104.2. Take this baby to, now this time to different, 240.6. And if you go to take this one, what's the next standard? Go to the next standard. What's the next standard? Overcam protection device. What's the next standard overcam protection device? 110. 110. So this panel will be 110 amp. I'm 110. Now here's the question where Nick would say, Chad, my panel is 125. Can I put an overcam protection device 110? Yep, but you have to size the conductor for 110 now. I mean, can I put my overcam protection device 125? Yep, but you have to size your conductor for 125. But that's the method I would like you guys to use, at least unless you're told otherwise. You go to this. Now my panel slightly has more amps than my overcam protection device. It's okay because of the standard sizes that they have. Okay, now the last one, guys, receptacle panel feeder. It's the same thing as secondary feeder for the transformer. So what I always say, match over current protection device, always. See the difference? The conductor that's going between the transformer and the panel always match the overcurrent protection device. So what's my overcurrent protection device? My overcurrent protection device, in this case, was 110 amp. Then I will take 110 amp. Alaribo, where do you take it? Take it to table 310.15 B16 under 75-degree column because it's three-phase system. And now, how many conductors and why? And what size? How many conductors? I need at least three-phase, right? And then I need a neutral because I have a neutral on the secondary side, a neutral. Should I pull full neutral? Absolutely. Anything 200 or less, full neutral. So this is a 4-conductor. Everybody knows why 4 conductors? Full neutral, 200 amp or less. What's the size? Number 2. Do I have a second? Second, okay. Number 2, A, W, G, T, H, H, N. And if you need to find the conduit, you get smart and you find the conduit for it. Done. Here's the conductor on the secondary side. The secondary conductors, secondary transformer, secondary conductors, or the panel feeder, right? Can you guys see how this is dual function? Has two things. This will be receptacle panel feeder, the feeder for the receptacle panel, and at the same time, it's actually the secondary feeder for the transformer. Number 2. Any question?
Why didn't we go to table 450.3b for step number 5?
You can. If you go there, what's your multiplier for step number 5?
1.25. So,
Same, almost the same.
so it's a wash?
Yeah. It's a wash. If you want, you can, that's where this will act as a continuous load for the circuit breaker as well as the, so if you want to, what's the table 2, 450.3b or 8?
B.
3b, yeah. You're absolutely right. It's the same. And if you go there, what does it say? Go up, right?
Yes.
Yeah. So what did we do? Went up. Either way, based on the secondary or based on continuous load for the panel. Same matches. Good point to write it there though. Thank you. It's a good point. Any question guys about this? Now can we size that system? Everybody, I think we're done with that one here. Yep. Before we go the next one, give you a break here. But before I leave here, can I have thumbs up that chat? We know any system like this, we know how to size it now based on these steps. Phil? Cool? Okay, before I leave guys, your homework, now you're gonna have a homework number 8. Your homework is, Chris, you don't have to mess around with the receptacles. I don't want the receptacles. All what I did, I gave you 105 kVA, already derated. And I want you, all these receptacle loads, 105 kVA. Demand, this is all demand. Can you guys, it's a demand. Does that mean, what does that mean if it's demand? Do I need to cut it, the first 10 cut it? The first 10 leave alone and cut? No, it's already demanded. So go find a transformer for this and size and do the 5 steps. Can I get you guys to understand? This is the first page. The first page, yep. Right to the first page. We at the bottom. Yeah.
Oh, it's at the top, the upper left-hand corner.
It's the upper left-hand corner, yep. In the first page. And it says, you say homework number 6, please change it to 8. And it's 105 kVA receptacle load, and I need you to do these 5 things. Can I have your attention for 1 second? I do not want you to derate the 105. Don't take the first 10. It's already done. This is all demand. Just do the 5 steps. Yes, sir.
So we're just skipping step number 2.
Right here. We're skipping 1 and 2. All these, I'm giving you this number. See that number 29? That's equivalent to this number. So these 2 steps are already done for you. I'm giving you equivalent to the 29.6. Can you guys write yourself a note? That's equivalent to 29.6 and go from there. Then you're going to go, the next step, Alaribo, the next thing you need to do is take this number that I gave you and find yourself a receptacle, not receptacle, a transformer, and continue.
It's really cool. Because they use disparity from one to the next.
Just go to the next. This is where you use your judgment, but for the exercise, please go to the next. Yep. Okay, can we have 5 minutes break, guys, and we'll continue with the UPS.
So the exercise for the next.
Go to the next, please. Okay, let's. If you guys switch, any question, guys, about transformers, matching a panel, and so forth? I think what we give you should be a typical. Always put the panels right next to each other within 25 feet. That method will apply. Okay, the second exercise I have, guys, is for PDUs. This is a little bit busy, so let me just try to make sense out of all this system. UPS PDU system, that's new concept. UPS PDU system. if you have data equipment like laptop servers and you're storing all this transaction of Home Depot nationwide, you need to be able to store all these data, digital data storage. If you lose power, you could lose all your data. So the Smarter Than Chad came up with this system. Let me start right in here. This is a server. This is your laptop, Chris. Right at the bottom here is your laptop. Your laptop, they want it, the Smarter the data guys want the server that store all the data about you, your shopping habit, your security clearance, whatever you want to do it, right into the server. They want to feed it, they want to make sure this server will never go down. So they have the following. They feed it from 2 PDUs. So they call it power distribution units. So the first time they go PDU1, PDU2. So that server, imagine guys, a laptop with 2 outlets like this. That's basically a laptop with 2 outlets, both tied to different sources. Okay, so that's what you're looking at. So you have an outlet coming from circuit number 1, an outlet coming from circuit number 1 here and here, PDU1, PDU2. The 2 PDUs are tied to 2 different UPS systems most of the time. In our case, we're tying them to the same PDU system, to the same UPS system, and then the whole system is fed from a panel. So what is a UPS? A UPS, guys, you take your AC, in this case 480, convert it to DC, close to 660 volt. So this is 660 volt DC coming from a 480. So you have, this is where you have conversion, right? To convert into DC. At the DC level, they go tied to batteries. You can see these are batteries. Right here is a bank of batteries. Did we go to, did we look at the batteries? We haven't seen the batteries yet, some of you. We will be going, when we go to, please, when we go to Allianz right here, guys, you're going to see exactly what we're looking at. So here's a UPS big box. Inside the box, there's a conversion mechanism that converts AC to DC. At the DC level, they go and tie a bank of batteries, a room like this, series and parallel, and they take 2 conductors, positive and negative, and they tie them right into the UPS system. So this is your bank of batteries, typically for 15 to 20 minutes worth of power at full load. It will give you, it will power all your system here for probably 10, 15 to 20 minutes, right in here. So they tie, then out of here, they go back from DC, invert back into AC, because we burn everything at AC. They invert into AC, and they have some type of a distribution section inside the UPS system. And from here, they feed multiple PDUs, PDU1 and PDU2. Cool? So the whole idea, guys, the whole idea, if the power is to go down right here in the high voltage panel, this will not see any interruption of the power because it's tied to 2 sources of power, a DC source and an AC source. So, and it's tied right here, tied all the time. They're not, you don't have to parallel. They're already tied at the DC level. It's like fire alarm panel. Remember that fire alarm panel that we were talking about yesterday? There's the batteries there. If the power is to go off, it alarmed that the power went off, and it continues functioning for a predetermined amount of time. Same thing, except big batteries. Okay, any question about how the system is made together? Physically, how you put them together. This is what you guys have, our system. We have our switch gear, and we took a feeder from the switch gear to feed our UPS system. From our UPS system, uninterruptible power supply, we took 2 feeders. One is going to feed the PDU1, one is going to feed the PDU2, and all these correlated numbers, hopefully they will correlate with the schematics or the wiring as well as the physical.
I think we have the transformer ahead of the UPS in the one, the examples that we
Yeah,
have in the lecture.
you're absolutely right. In Revit, we were not able to find the UPS with a transformer. That's why I asked you guys to do it this way. In real life, the transformer will be actually part of the PDUs. The PDU itself will have a transformer. Can you see the transformer here that you looked at for? That transformer in real life will be in a box with the PDUs. They have one big box that take the voltage here, 480, transform it to 28120, and distribute it to all the loads. Yes, Nick?
Can you explain a little bit more about PDU?
PDUs, power distribution units. Power distribution units take all the power from here and distribute it to all these servers. So imagine this. Imagine the racks and racks. All this room is full of racks of servers. Each rack has, say, 6 servers. So here's a rack from top to bottom to 7 feet. Inside it, there was, say, 5 servers. Server 1, 2, 3, 4, 5. Each server will be plugged into multi-out assembly here. 1, 2, 3, 4, 5. From this side will be the same server will be plugged into 1, 2, 3, 4, 5. So every server will have 2 plugs all the way. These plugs will be underground. The multi-out assembly will be plugged into a receptacle under the floor, and that receptacle will be fed from PDU 1, that's circuit 1, from PDU 2, circuit 2. So they have dual fed to that server rack. So what you're looking at here, I see a server, that could be server rack. Technically, it's actually almost 5 servers. They have so many technologies. In a rack, 1, 2, 3, 4, 5, plugged into both sides on a multi-out assembly. Multi-out assembly are plugged into underground, underfloor receptacle. The underfloor receptacles are going to feed from a 20 amp circuit. These are 20 amp circuits. 20 amp circuit that's coming from 2 different PDUs. Now, what's the difference between a PDU and a panel, Chad? Right? Well, it looks like this panel, right? The difference between a PDU and a panel, guys, is a major difference. A PDU is like a substation. It has a transformer inside it. Almost always, they come up with a transformer inside it. So you take the 480 into 280. That's major. The second one, they have, they call it 200. I call it right here, 200% neutral. So they size the neutral double the phase because of harmonics. So long story short, as far as you're concerned, in the PDUs, they solve the problem of harmonics that's coming out of these servers. These servers are heavy harmonic loads that could screw up your system. So they filter the harmonics right here, the harmonic that's coming to the server and the harmonics that are reflected back into the system. So they solve the problem of harmonics from the loads. They have a transformer. They solve the problem of harmonics by filters and doubling the neutral. So that's it, really. Other than that, it's a unit. This is what we call it, unit substation. Remember how we said unit substation? It's exactly a unit substation, except, well, 480 to 8. Yes.
And then, does the server know, the server's getting power from, let's say.
Server doesn't care and doesn't know.
It doesn't know?
It doesn't know which power, as far as his, say if this server was 10 amps, 5 amps will come from here, and 5 amps will come from here. That's what the server cares.
Oh, yeah.
They're DC. It's taking, it's taking it at the AC level, and deep inside here, the way they time that is this conversion here, and another transformer, a little bit conversion here, and then right in here, it's a DC level. So the server is a DC. So they have 2 sources at the DC level that they dump it into the server. It's connected right here. The 2 are connected to the server at the DC level, though. It's like paralleling.
Then if one goes down.
Thank you. Now, here's what happened. Now this baby drops down. This double to what? 10 amps. Nothing will happen. Now, in my example, if the UPS goes down, I am a dead. But what they do in real project, guys, they take this circuit breaker here and feed it from a completely different UPS system. From a UPS, from another different UPS.
So they feed each PDU
from a different UPS. Then if the UPS goes to hell in this side, you still have another UPS. They go. I'm gonna let Guy here when he comes. He's our expert in the PDUs. Talk about all this redundancy. You can, and then there's generators here too. And so this is just sizing him. It's coming, guys, when we go into the power system. Any question about this system though? So I have a 480 switch gear feeding a UPS that's 480. From the UPS, I'm feeding a 28120, 28120 PDUs. Where's the transformer like Chris did? The transformer happened inside the PDU in real life. In our project, we dropped it outside for CAD, for Revit.
What's this? It seems rather ridiculous to take, you've got AC DC up in the very upper left-hand corner.
Yeah.
Your end game is to feed 2 machines.
Why can't you feed with DC?
12-volt DC.
Yeah.
What I'm used to seeing in telecom, which is basically computers.
Yeah.
They just have, they use typically a 48-volt DC, but it's the same thing. They take it once,
and that's it.
Yeah, and it's nuts to keep
Yes.
doing all that stuff.
There is and I'm not an expert in the server business. There is a move, if you read about them, to actually all this junk that you said. Absolutely. Why can't we jump right here to the right voltage and burn our servers at 480 or 24 volt DC? As of now, that would be a good question for the. I think the only different thing I can tell you between, and I'm not expert in telecommunication system, the only different thing that I've been told for this is a huge amount of load. This is very high load, as in you can have 2,000 kVA load. It's a huge amount of load, data load. But there is a move of feeding things from the DC right here. Why to do DC twice? Every time you go DC to AC and vice versa, guys, you lose. Okay, good point though. Any question, guys, about the system, how the system is put together? Any question how the system is put together? So what do we need to do? We need to size the following. Number one, the UPS. Number two, the overcapacity device for the UPS. Number three, the conductor that feed the UPS. Number four, where's number four? We're gonna the PDU itself. Number five, the overcapacity device for the PDU. The feeder that feeds the PDU, typical for both of them. And number, that's it, right? That's the number of 6 things that we need to size for this system. Any question?
What about grounding?
Not, yes, we can, but not now. You can go ahead and, grounding is like any other panel, guys. Really not a whole lot to it. Okay, we just specifying it. Okay, the first thing I would like you guys to do is, the first thing we need to do is power factor. Here's a couple of assumptions. A couple of assumptions that you need to take. We need to take the computer room. In order to size a UPS, we size it based on the computer load. The computer load is a function of the computer room. I decided for this to have a 20 by 20 computer room. I have my UPS, my PDU in it. These are all my servers. Data center power. Assumption is 80% power factor. Power density for this data center is nothing. It's 30 watt per square foot, nothing. So based on this, here's the rule that I'm going to be doing. SF stands for the square foot of the data. Density stands for the density right in here. And and power factor divided by 1,000, that will get you the kVA of the UPS system. kVA of your UPS system. I like to always, I'm going to add here, guys, if you multiply 1.25, that factor, add 25%, it will add a 25% for continuous load for you, as well as efficiency of the system and so forth. This factor is Chad's factor. So you add this 1.25 at the end, will you? To accommodate for continuous load, losses in the system, and so forth. Any question, guys, about how this system works? So how do we size this? We size it based on the square foot of the building. So let's go ahead and start sizing. The first thing we need to do is, did we have a PDU? Okay. So we have our PDUs. Let's go start sizing. I need somebody to help me with this. So 20 by 20. Where does the 20 by 20 come from? Square foot of the computer room. Density. What's the density? The watt per square foot. How many watts per square foot you can jam into this data center? And this is always a function of cooling, guys. The problem is cooling them. You need to keep them cool. Okay, 30. Multiplied by 1.25, accommodate for continuous load and losses and so forth in this, okay? And divide by a power factor, assuming worst power factor 0.8, and divide by 1,000, so because I want to size everything based on 1,000. And if you do that, mine is wrong because I did not multiply by a power factor. Can you guys give me the answer?
18.75.
18.75. A second? 18.75 kVA. Do I have a second? second. Okay. 18.75 kVA. Any question guys about this? There are two ways of doing it. You do it this way, that's the engineering way, or the other way, go to every single server, find the amps on the server, input amps, multiply by the voltage, multiply by 1.25 for continuous load, and add them up. But we don't know what the servers are, so that's kind of an acceptable rule. Right now, if you talk to a guy here, guys will tell you this number is 200 watt per square foot now. So if it's 200, would anything change other than the calculation? The method stays the same. You just put 200 instead of 30. Okay? Any question about 18.75 kVA? And why did I, because this is watt, I converted to volt amp because we size things in volt amps. Any question before I move to next step? So my UPS size is 18.75. There's one little problem though. I need to find the actual size of the UPS. The actual size of the UPS. The actual size of the UPS, guys, I'm going to put it right in here. I gave you a sheet. You guys remember the sheet that I gave you? Typical. It might not be accurate 100%. Can you flash that sheet that I gave you guys? That sheet that had generator size on one side, on the other side it has a UPS and PDU size. If you guys grab that sheet that had generator size. Okay, so if you go to this, I have 18.75. I'm going to call it DeWalt. I put it at DeWalt. I ask you guys to write them at DeWalt 7- or 6-12, right? I'm going to say 3-13. 3-13. 3-13. And please look at that sheet that I gave you. If you don't have it, I should make you a copy of it. If you go there, my next standard for this one would be, I have 16, 8, 10, 12, okay, I have 40, 60, 80. So the smallest that I can buy, from that sheet, did you guys get the sheet? Is 40, right? Smallest that I can buy is 40. So I have a 40 kVA. 40 kVA. The smallest I can buy is 40. At least this size. I'm sure there's other sizes, but for the sake of the calculation, these are the numbers we're going to use. If you guys go to manufacturer of UPS, they have a list of all the sizes, technical sizes that they have. And from there you can find the actual size. Okay, so I size my 40 kVA. Any question about the 40 kVA? All right, so now we know what the size is. Let's go size the rest of them. Since we're dealing with 40, take the 40 here, kVA, divide this baby by 1.73 times 480. I'm sizing the overcompression device for that baby. And that will give me 48, right, Chris? 48 amps. And I'm going to assume it's continuous load, so multiply by 1.25 times the overcompression device. 1.25 times 48. And that will give me 60 amps. And if you take the 60 amps, take it to 240.6. If it's not a standard, go up, but it's actually 60 amp is a standard. That's it. So I have a 60 amp overcompression device on the primary side of the UPS. Cool? UPS feeder, guys, is the same thing. 1.25, multiply it by 480, same, almost match the overcompression device, equals 60 amp. And then you take your 60 amp, to table 310.15B16 on the 75-degree column. If you took that one, it will give you, where am I here, chats? 3 conductors. How many conductors? 3 conductors. Number 6, A, W, G, T, H, H, N, or Most likely THHN. Why 3 conductor, Chris? Because I'm not bringing a neutral to the UPS. No need to bring a neutral. You bring just 3 phases to the UPS because you create your own neutral later on. It's like the transformer for the receptacles. We don't bring a neutral to feed the transformer that feed receptacle. We create our own neutral. Okay, so I can almost say match over computation device, right? Almost. But we're sizing based on continuous load. Any question, guys, about the primary? This is the UPS over computation device and the UPS feeder. Now, Chris, if you go to PC, I think, I haven't dealt with them for a while. Any manufacturer of UPS, William, or PDUs, and you find that there is no 40 kVA, there is a 35 kVA, would that process change? No, you just put, instead of 40, you put 35 and you do the calculation. If the manufacturer of the UPS system told you that they need you to stick a 50 amp fuse here or circuit breaker, what would you do? You put a 50 amp circuit breaker. Unless you know otherwise, that's how you do it. So when we start the design, Chris, we have no idea what product we're buying. That's the process that we start. When we know the material, if we discover the manufacturer of this product, they really want us to put 70 here, we go ahead and put 70. Manufacturer's rule. Or they want the feeder to it to be number 1 instead of number 6. You go there and put number 1. Most of the time, guys, they're going to follow these rules, so you're not going to be off. Okay, so let's go back to, or forward to PDUs. Now we're going to go to the PDU power distribution units. We're going to size the power distribution unit. Chris, we're going to do it the same way. Please multiply this by 1.25 for losses, continuous load, and so forth. We're going to basically repeat the same process here for the PDUs. It's 20 times 20 for the PDU times 30 divided by 0.8 times 1,000 to make a kVA multiplied by 1.25. And what did we come up? 18.75, Chris? kVA. 18.75. The same size like we did UPS. Now we have 2 PDUs. These 2 PDUs will be redundant, so they will be the same size. So this size actually will be the same. They don't share, they share the load equally, so 50% of them will be loaded, but we want to size them based on redundancy, just in case one of them goes wacko, the other will pick up the load. Okay? So we got the PDUs. Now let's go size, take the 18 again, 18.75. Go to DeWalt, where you guys supposed to have written it. What is it? Aladibo, 13? 3-13. You go there, and this is where you should have put these. What's an standard? I guess it's 40, right? The same 40 kVA. So Chad, why did you repeat yourself here? I tell you why I repeat myself. Because if you go to an actual manufacturer and the PDUs were different sizes, you're supposed to go check with the manufacturer. Then the process will be different. So right now, for the sake of the calculation and make it, because we're a class, students, these are good enough for us. The numbers are good enough, but that could be different. The PDU and the UPS sizes, guys, could be completely different. But we need to standardize somehow on one size, so I gave you these numbers to play with, which is good enough. These are not industry sizes, but other manufacturer might have different sizes. Okay, so we got this one, piece of cake, right? Everybody get that size, 40 kVA. Now PDU over computation device. PDU over computation device, the PDU guys over computation device number 5, you're going to take the 40 K divided by 1.73. What is the input of the PDU? What's voltage? 480. We're still at the 480 volt. We're not yet at the 208. So if you go there, it'll give you 48 amps. We did that. Now, Chris, I go to 450.3B. Why? Because remember, there's a transformer. There is a transformer inside the PDU. I want to allow the transformer to start without tripping it. So I use this multiplier. I do 2.5. 2.5 because of the transformer from this table, multiplied by 480. Oops, not 480, 448. And that, if we did that one, that will give me 120 amp. Cool. Then you take the 120 amp, take this one to 240.6. What's the next standard down? The next standard down is 110, right? 110 amp. The next standard down is 110. Why down? Because if you go to this table, we talked about this neck, it doesn't allow you to go up. Why did I size the overcome protection device for this particular one higher? Because of the air rush. Because of the air rush. Okay, let's go to the number 6, guys. Is a PDU feeder. The same thing. You take the 480 amps, the feeder to the PDU, and then we need to multiply it by 1.25 continuous load 480. I thought we did that one. 48, right? Did they say 480?
You're saying it wrong, but right.
What do you call this? Dyslexic, or no? That's not dyslexic. That's
It's called Chad.
Chadixic,
There you go.
or Rymanizing and Chadizing, or Kirgizing, or whatever we call it. Anyway, 480. 1.25 times 480. What is it? 60? 60 amp. Thank you. Then you take your healthy 60 amps and you take it to table B10.15, B16, 75 degree column. How many conductors we need for this baby? 3 conductors. Why 3 conductors? I don't need neutral yet. I'm still carrying 480. 3 conductors, and what size?
6.
Number 6. Number 6 AWG THHN. Done. 3 conductors. Number 6. Coming out of the UPS, Chris, to the PD, to every PDU. We have 2 of them, redundant. So they're all going to be the same size. I did 1 PDU, guys. What do you think the other PDU is going to be? Redundant. This is what you guys are going to be doing for your project when you size the PDUs. Exactly the same criteria. Any question about number 6 before I move to number 7? We're good? We don't have number 7?
No.
Oops. We're done. So let's go back and review with all this stuff, guys. We're done. Number 7 is going to be okay. So if you look what we did, we sized the UPS, the feeder to the UPS and overcome protection device. Then we sized the PDU, the feeder to the feeder that feeds the PDU and overcome protection device. And then it's done. Now, what we didn't size here, guys, is the panel and this side. Chris, when you go to, I have to make you guys a cut sheet about PDU. I'll have a cut sheet about PDU. When you get the 40 kVA PDU, in the 40 kVA PDU, guys, it will give you a size of a panel. Inside that size, give you a panel size. So say it's a 100 amp panel that's going to be tied to it, and how many circuit breakers you want in this PDU. So when you guys pick the PDU, you have inside the PDU, it will give you the standard sizes panel that goes with it. That's why we didn't mess with what's inside here, and what's like these all will be 20 amps guaranteed. There will be 20 amp branch circuits, and in this case, if it's what did we say the PDU is 40? It's like a transformer. If you take 40, what's the full load current on the 208 on the transformer 40? 40 kVA. That was, we just were there, guys, a second ago. 7-7, right? Can you go to 7-7, please? 7-7. Okay, so if I have 40, I don't have 40, so I have 45, say. Most likely it's going to be like a 100 amp panel coming out of it, close to 100 amp, 125 amp panel tied to it. We do not size the panel that tied to the PDU. PDU comes a panel with a certain main and circuit breaker as well as the transformer all in one big fat box. You size the input to the PDUs, but not the PDUs themselves, not the distribution panel. But I want you, William, to understand, when you size the PDU, you just size the transformer and you size the overcurrent protection on the transformer and the panel with an overcurrent protection device in it. Revit PDUs that you guys have, Revit PDUs have basically the overcurrent protection device and the panel. It's just a panel. They don't have a transformer in them. It's just the families. It's not related. Hey, Rob. Fine. Okay, the last thing, guys, will be homework number 9. Please change this one into homework number 9. Homework number 9. Homework number 9 is the following. Can you guys change this one to 9? Okay. I have a room of 30 by 30, square room. I want to put servers in it, and I talked to the computer engineers like Chris, and they told me that the density that we can rack in that baby is 100 watt per square foot, not 30, 100. The power factor assumption, I'm going to continue worst scenario 80. And I need to size UPS and PDU system. Basically repeat the 5 steps or the 6 steps for the PDUs and the UPS. Can any questions about the homework? Straightforward. Do me a favor. With this knowledge, guys, would you be able right now to size the transformer for your project that feed the receptacle and the PDUs? You should be able to take this one directly to your project and size your PDUs, feeder for the PDUs, as well as the UPS, as well as the transformer that feed the receptacle panel. Am I right, Dustin? Would that help a little bit? Okay. What was the, I think it's 90 watt per square foot. Is that what we changed ours? Our data center is 90. The project, 90. And you take the square foot of that computer room for our project. Any question is about PDUs, UPS, and panel/transformer matching?
Project is 30 watts per square.
I think when can you guys change this one to 90? I think that's what we did when.
Well, he wrote down 150.
Did he? Okay. Did he write 150? Okay. Let's do it. Can you guys, our project change it? I think that's to 150. The project to 150. Make sure you go to your calculation and change this one. I have to write myself a note here. Okay.